Hello everyone. Today we are going to be looking at part 2 of complex vector spaces. In here, I'll be covering the following: a quick recap of complex vector space, then I'll do examples to show that vectors which are in this complex vector space are linearly independent, dependent, or they can form a basis for the complex vector spaces. So let's start with the definition of a complex vector space. Okay, a vector space is a non-empty set V of objects called vectors, on which are defined two operations called addition and multiplication by scalars. Now, as we are in the complex vector space, the vectors as well as the scalars are going to be complex numbers. They are all these vectors in the non-empty set V are subject to the 10 axioms or the rules, and these 10 axioms, we have seen them many times before. The main important part is that for a complex vector space, the vectors and the scalars are all complex numbers. We will be specifically looking at complex vector spaces of type C to the power n here. So if V, C to the n, is called a complex vector space on n-ordered tuples, where the vector addition and scalar multiplication is defined as. So if I take two vectors u(n), v in Cn, so u will be vectors u1, u2 up to un, v1, v2, vn. Important fact is the ui's and the vi's are complex numbers. Then if I add these two vectors in Cn, u plus v, then basically I'm adding the components. So u1 with v1, u2 with v2, dot, 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 and un with vn. In a similar fashion, the scalar multiplication is if alpha is a scalar. Now remember, once again, it's a complex number. Then alpha times u is alpha times u1, alpha times u2, alpha times un. Very simple example I can just talk about here is, suppose u is an element of, say, 1i minus 3. So this u is an element of C3. Now if I do, say, alpha times u, suppose my alpha is I. So alpha times u would be what? I times the element 1i minus 3. And if you guys remember that we have done a review of complex numbers in the first session, so you just use those properties. So this would be I with an I square is minus 1, then I with I square again minus 1, minus 3i. So this will be minus 1 minus 3i. Okay, so now let's look at some examples. The first example would be an example related to linear dependence. The question says, prove that the set S, which consists of element 1 and I minus 1, is linearly dependent in C2. Now I'm writing like 1 and I like this just to make save space. This 1i can also be written as 1 and I. It's just to save space I'm writing it here. Okay, so I want to prove that this is linearly dependent. So according to the definition of linear dependence, we need to find two scalars, C1 and C2, not all 0, such that when C1 multiplied by 1 plus 1 and I plus C2 multiplied to I minus 1, here, equals 0. Okay, so what we do is, as we have been doing so previously, that is basically we look at, if you want to find the scalar C1 and C2, okay, so we take the 1 and I minus 1, we put it in a matrix and apply the row reduction algorithm. And when you do that, what happens is, so I apply the elementary operation R2 minus I times R1. Because remember, I want to make this to be 0. So when you make this to be 0, that is, you have to multiply the top row with I, and R1, and then the result goes in row 2. When you do that, what do you get? You get a bunch of zeros because, let's look at this one, R2 minus I, R1. Now I, when you multiply with minus, I gets 0, minus 1. I'm talking about this one scenario here. And when added to, it's a minus of I within I. So what does this make? I'm talking about this little value. So it is minus 1 plus 1. Makes it a 0. Okay, so now going back to the things we did in our chapter 1 of this book, we find that there is only one pivot column. This is the only pivot column. So clearly the set is linearly dependent in C2. Now that's going by the methods we have learned, or if you could also see it, that if you look at these two elements, another way of looking at it is when you put it in this form, you can also eyeball it and say, hey, when I put C2 to be, sorry, this has to be I want to make C1 and C2 be such scalars, and they are going to be complex numbers also now, such that when I multiply C1 with the vector 1 and I, and C2 with I minus 1, I should get 0. So the first one, this top can be a 0 when C2 is I, because I times I squared is minus 1, and if C1 is 1, 1 minus 1 becomes 0. Similarly, this I here, when C2 is I times minus 1 is minus I minus I makes it a 0. So if you can see it easily, then you can do this way, or the best way is the things we have learned. We can use that method too. Okay. Now let's go ahead and look at linear independence, kind of a problem, and see what we get here. Okay, the question is the set 1, I, 1 plus I, so clearly this is a vector in C3, another vector 0, I minus I, and the third vector 0, 0, 1, is it linearly independent in C3 because these elements have 3 rows. So what are we going to do is apply the definition of linear independence. Now, when you're applying the definition of linear independence, remember again we need to find 3 scalars such that this linear combination is 0, but with a very specific condition that all the scalars C1, C2, C3 have to be 0. Okay, either you can literally go ahead and open this matrix, this linear combination, do all the solving of the linear system, or we can apply the things we just learned earlier in the previous slide. That is, we write these vectors 1 I 1 plus I, 0 I minus I, 0, 0, 1, and try to prove that all the columns over here become pivot columns. If that happens, then clearly this set is linearly independent. So let's apply the row reduction algorithm on this matrix. So the first thing we have to do is we have to make in the first column the second and the third element to be 0. We can do that by R2 minus I, R1 to R2, and then R3 minus 1 plus I times R1 to R3. When you do that, we get this matrix 1, 0, 0, 0, I, 0, 0 minus I, 1. Okay, now the first column is a pivot column, so this second one becomes a pivot column, and this is the pivot. So we need to make this element minus I to be 0. And simply R2 plus R3 goes to R3. And what we happen to get is every column is a pivot column. Clearly my set S is linearly independent in C3. Let's talk about bases. The question says, is the set S, which combines of 2 elements, 1 and minus I, and you're going to write like this, and I and 1, a basis for C2? Okay. Now keep in mind, okay, so a little things to talk about. First of all, the dimension of C2 is 2. Now, if the dimension is C2, and this is a theory we have learned, that any set of two linearly independent vectors in C2 will form a basis. So what we have to do is, if these two elements 1 minus I1 are linearly independent, then automatically the set S will become a basis. So once again, we write down the matrix 1 minus I1, apply the row elementary operation. And what we see is when we apply this row elementary operation, we get only one pivot column. So the set is linearly dependent, and hence this set is not a basis for C2. One more example. We would like to write a vector minus I, 2 plus I, minus 1 as a linear combination of the following basis vectors: 1, 0, 0, 1, 1, 0, 0, 0, 1 plus I. So they said this is a basis vector. And looking from these vectors, clearly we can see that these vectors, all of these vectors are in C3. Now keep in mind, C3 means the dimension of C3 is 3. And if it says this is a basis vector, that means every vector in C3 can be written as a linear combination of these three vectors. Not only that, but all these three vectors are linearly independent. Okay, but the question here is saying is, we would like to write this vector, any vector here in C3, as a linear combination of these basis vectors. So basically we want to like this vector, we like to know what will be the scalars alpha, beta, and gamma. And these alpha, beta, gamma, remember, they can be scalars. Now, they're scalars, they can be complex numbers also. So what we're going to do is basically not just solve this system of equations we get from this one, alpha plus beta is minus I. The next one gives beta to be 2 plus I. So basically beta is solved for us. And then 1 plus I gamma equals minus 1. Okay, so remember you have to write it as a scalar. So alpha plus beta is minus I. So beta is 2 plus I. Plugging this in this equation, we get alpha to be minus 2I. Just plug it in over here, guys. Now let's look at this one. 1 plus I gamma equals minus 1. So gamma is basically minus 1 over 1 plus I. Remember, you have, this is a number, but you have to write a proper complex number. A complex number, guys, if you remember, a complex number is not as a z equals a plus ib. That's how a complex number is written. This gamma is not written in the proper form of a complex number. You have to change this. And if you remember the operations, that is, this is basically writing down, you're finding the you will have to find this in this form. So what you're going to do is you're basically doing the division here. So here is, so you're going to write in the form as, you want to get rid of this 1 plus I, which is in the denominator. And you do that by multiplying by the complex conjugate of this one. So it's 1 minus I, 1 minus I. Then you can do some your math here. When you do the simple math, you get the gamma to be negative 0.5 plus 0.5i. Now this is written in a proper complex number. Thank you.